Hi everyone. Today we are building a project from scratch, and the project is building a transformer. Specifically, we are tackling the infamous or famous, I won't say it's infamous, sorry, famous paper on transformers is all you need. It's thanks to that paper from our talented people at Google Brain that we are able to have ChatGPT today. So you might have seen ChatGPT, I'm pretty sure, and it's so powerful that it can be used for many generic tasks. So today we'll be understanding how this whole technology of transformers work. And for our viewers out there, for some context, transformers are a type of neural networks that are optimized for natural language processing. I digress a bit, but transformers are sort of an upgrade over recurrent neural networks. And the idea is recurrent neural networks was also an improvement over generic neural networks like your general neural net, like the neural networks which the multi-layer perceptron. So the multi-layer perceptron generates a word, but it doesn't really keep track of what words that come before it. So how RNS built on top of that is that they also keep track of like sort of a memory of what has happened in the past to let each word generation depend on what has happened in the past. The problem is with this sequential memory, in a sense, for you to decide what word to generate next for word 3, you need to pre-calculate the hidden states and the words for word 2. And for word 2, you have to calculate the hidden states and the word for word 1. So what that meant was it's hard for us to train our neural networks to really it's very hard to train a neural network at scale. For us to train the hidden states for stage 3, you must train stage 2, and so on and so forth. So it wasn't a scalable way of training it. So our smart people um, then realized that, oh, I guess RNNs too also have this thing called attention. And attention is, like its name suggests, it is really a glorified weighted vector of numbers that tells us how much should a word pay attention to other words in the sentence. So what they realized, the Google Brain smart people realize, is that you don't really need the hidden states. All you need is these transformers, and these attention. So the Google Brain people realized that these attention arrays are really what all they need. You don't really need the hidden states for the neural network to understand what has happened in the past and in the future, like it's bidirectional now. And of course, these arrays they don't really pay attention to the information of the position. So they added another thing called positional embeddings, which we will go through later. But in summary, transformers built on top of RNNs by allowing training of these attention layers in parallel. There's no need for us to train the first few stages, the first few hidden states before we move on to the next, and they just remove that completely. And they realize that they're able to suddenly train this model at scale on huge corpus of data much more efficiently in parallel, and it start to work. So it's really cool. It's really cool, and of course, there's way more optimizations. Like this explanation of mine, it's not that refined. But for today, we are going to better understand this. Personally, for me, I have never built a full transformer from scratch. Not that we need to, because OpenAI do have their APIs to connect to their text DaVinci model as well as use ChatGPT by itself on their UI. So we don't need to know that, but we don't really need to know the underlying implementation, but I thought why not do a deeper dive to better understand the moving parts of it. So for today, we are watching this video, Let's Build GPT from Scratch in code spelled out. And it's recommended by a dear colleague of mine. And today I'll be videoing myself building this and understanding the process behind that. I would make this video as organic as possible by showing exactly what I do in understanding this. So YouTube, videoing, Googling, using Copilot is all on the table. And I hope that this video would give our viewers some support that look like it's totally normal to make mistakes during the process. And yeah, and I'll get a chance to share my thought process. And with that, let's get started.
Hi everyone. So by now you have probably heard of ChatGPT. It has taken the world and the AI community by storm. And it is a system that allows you to interact with an AI and give it text-based tasks. So for example, we can ask ChatGPT to write us a small haiku about how important it is that people understand AI, and then they can use it to improve the world and make it more prosperous. So when we run this, AI knowledge brings prosperity for all to see, embrace its power. Okay, not bad. And so you could see that ChatGPT went from left to right and generated all these words sort of sequentially. Now, I asked it already the exact same prompt a little bit earlier, and it generated a slightly different outcome. AI's power to grow, ignorance holds us back, learn, prosperity waits. So pretty good in both cases and slightly different. So you can see that ChatGPT is a probabilistic system, and for any one prompt, it can give us multiple answers, sort of replying to it. Now, this is just one example of a prompt. People have come up with many, many examples, and there are entire websites that index interactions with ChatGPT. And so many of them are quite humorous. Explain HTML to me like I'm a dog. Write release notes for chess 2. Write a note about Elon Musk buying a Twitter, and so on. So as an example, please write a breaking news article about a leaf falling from a tree. In a shocking turn of events, a leaf has fallen from a tree in the local park. Witnesses report that the leaf, which was previously attached to a branch of a tree, detached itself and fell to the ground. Very dramatic. So you can see that this is a pretty remarkable system, and it is what we call a language model, because it models the sequence of words or characters or tokens more generally, and it knows how sort of words follow each other in English language. And so from its perspective, what it is doing is it is completing the sequence. So I give it the start of a sequence, and it completes the sequence with the outcome. And so it's a language model in that sense. Now, I would like to focus on the under the hood components of what makes ChatGPT work. So what is the neural network under the hood that models the sequence of these words? And that comes from this paper called Attention is All You Need. In 2017, a landmark paper in AI that produced and proposed the transformer architecture. So GPT is short for generatively pre-trained transformer. So transformer is the neural net that actually does all the heavy lifting under the hood. It comes from this paper in 2017. Now, if you read this paper, this reads like a pretty random machine translation paper, and that's because I think the authors didn't fully anticipate the impact that the transformer would have on the field. And this architecture that they produced in the context of machine translation, in their case, actually ended up taking over the rest of AI in the next 5 years after. And so this architecture, with minor changes, was copy-pasted into a huge amount of applications in AI in more recent years. And that includes at the core of ChatGPT. Now, what I'd like to do now is I'd like to build out something like ChatGPT. But we're not going to be able to, of course, reproduce ChatGPT. This is a very serious production-grade system. It is trained on a good chunk of internet, and then there's a lot of pre-training and fine-tuning stages to it, and so it's very complicated. What I'd like to focus on is just to train a transformer-based language model. And in our case, it's going to be a character-level language model. I still think that is very educational with respect to how these systems work. So I don't want to train on a chunk of internet. We need a smaller dataset. In this case, I propose that we work with my favorite toy dataset. It's called Tiny Shakespeare. And what it is basically, it's a concatenation of all of the works of Shakespeare, in my understanding. And so this is all of Shakespeare in a single file. This file is about 1 megabyte, and it's just all of Shakespeare. And what we are going to do now is we're going to basically model how these characters follow each other. So for example, given a chunk of these characters, like this, given some context of characters in the past, the transformer neural network will look at the characters that I've highlighted and is going to predict that G is likely to come next in the sequence. And it's going to do that because we're going to train that transformer on Shakespeare. And it's just going to try to produce character sequences that look like this. And in that process, it's going to model all the patterns inside this data. So once we've trained the system, I'd just like to give you a preview, we can generate infinite Shakespeare. And of course, it's a fake thing that looks kind of like Shakespeare. Apologies for, there's some jank that I'm not able to resolve in here, but you can see how this is going character by character, and it's kind of like predicting Shakespeare-like language. So, verily, my lord, the sights have left thee again, the king, coming with my curses with precious pale. And then Tranio says something else, etc.
Something pretty important about this detail is that Andrej is generating the words character by character, and it does matter. Sometimes we can make the transformer generate words token by token, and token is like a partial word of sorts consisting of multiple characters. But in this case, Andrej seems to be generating them character by character instead. So what would be the repercussions? The attention works in a way such that every single token, the token can be, I guess in this case, like a position, for every single position here, you have your own attention array. And if every single position has its own attention array, the size of all other positions, then we can see that the memory is going to scale quadratically. If you have 10 positions and each position has an attention array of 10, then you're going to have 10 times 10 for the memory that you use. So if you're going to use characters over having each position represent a partial word, which is what GPT-3 uses for their tokenization strategy, this approach of character-based tokens is going to be more expensive in memory. Yes, so let's see how Andrej does it anyway, and let's continue.
And this is just coming out of the transformer in a very similar manner as it would come out in ChatGPT. In our case, character by character. In ChatGPT, it's coming out on a token by token level, and tokens are these sort of like little subword pieces. So they're not word level, they're kind of like word chunk level. And now I've already written this entire code to train these transformers, and it is in a GitHub repository that you can find, and it's called NanoGPT. So NanoGPT is a repository that you can find on my GitHub, and it's a repository for training transformers on any given text. And what I think is,
I did not know about NanoGPT. I find this pretty surprising. Okay, I'm sorry, viewers. If you see me pausing, it's because I personally notice things that are surprising. My personal rule of thumb when building projects and watching tutorials is I will look out for things that are surprising to me. So if it is surprising to me, I tend to pause a lot. I'm sorry, but if you like to fast forward, please go ahead. But yeah, let's see. According to the screenshot, it says the simplest, fastest repository for training, fine-tuning medium-sized GPTs. Okay, training. Okay, I'm pretty surprised. Okay. Okay, training is where we train all the layers in the transformer, and fine-tuning is, I mean, for training we typically use a way larger set of data, maybe millions and billions of words in text corpuses to train that. And usually training GPT from scratch is real expensive, and OpenAI and our big AI companies like Google Brain, Anthropic, they took a hit for us by training one for us. It takes a lot of money. Yeah, unfortunately, we use a lot of matrix multiplication, and that is very CPU intensive or GPU intensive. And the second thing, fine tuning is typically more common among typical smaller companies where they do not have the money to train the whole thing from scratch, but they have the money and the resources to take an existing model that is already trained, like what OpenAI allows us to do. Um, and we can provide examples in the order of hundreds to fine tune the final layers of that transformer to make it better at a specific task. So I like to think of this as an analogy where training is analogous to like teaching a child from scratch to high school, and they know like things in general. And I like to think of fine tuning as like additional training where we train this high school student to do a specific task with some additional examples. And because this high school student has really painstakingly understood the fundamentals of mathematics, English, and stuff, we don't really need as many examples to train this high school student to be good at a task versus maybe training a child. So I hope that analogy is helpful. Um, Nano GPT, simplest, fastest repository for training, fine-tuning medium-sized GPT. Okay, my question now to myself is, what do you mean by medium-sized? Exactly how many um, parameters are you talking about? Okay, so it's a rewrite of min GPT that prioritizes teeth over what I don't understand what that means, but still under active development. But currently the train file reproduces GPT-2. Oh, okay, that's a nice. I guess that answers my question about 124 million parameters, which is not a lot. To put it in perspective, if I'm not mistaken, Curie is about 7 billion. Curie should be about 7 billion. Open AI sizes. Yes. So we. Oh wait, this Azure, but Microsoft bought over. It's not really bought over, but they funded OpenAI, so I guess I could have used that. But we can see that Ada is about. Whoa, wait, what? Where's that number? Okay. But you can see that. Okay, this is not great. Where's OpenAI's model size? Yes, where's the model? Finding the right model. There it is. Wow, where is that? Adder. Didn't you mention the parameters? Parameter detail. Oh, that's not the. No, that's not. Size of model. Wow, I'm surprised that they didn't. I'm pretty sure they leave it somewhere, just maybe not looking at the right place. Let's check in the models part. What? They didn't mention the size here? Hey man, why didn't you place the size here? That's so weird. Okay, let's just size of text DaVinci GPT OpenAI. Aha, yes, this one. Yeah, so as you can see, like the largest DaVinci one is about 175 billion parameters, and we saw from this that this is about 124 million, so it's really much smaller, about 1,000 times smaller for a medium-sized GPT. So okay, so they have a train.py file for training a GPT model. That's pretty nice. This is pretty helpful. I think, wow, okay. I didn't know that this repository existed. And this is huge because traditionally for us consumers, we would call an API to OpenAI to fine-tune stuff and train stuff, but people are so nice to upload this repository to expose a similar training code for the training loop. So we can technically train something without having to rely on OpenAI or guess our own implementation of training the GPT or coming up with it from scratch. So it's really reassuring that Andre mentioned this GitHub profile. Anyway, let's continue.
Is interesting about it because there's many ways to train transformers, but this is a very simple implementation. So it's just two files of 300 lines of code each. One file defines the GPT model, the transformer, and one file trains it on some given text dataset. And here I'm showing that if you train it on an open web text dataset, which is a fairly large dataset of web pages, then I reproduce the performance of GPT-2. So GPT-2 is an early version.
I didn't notice this, but this Kapati is by Andre. Oh, okay, that's so nice of him.
Of OpenAI's GPT from 2017, if I recall correctly. And I've only so far reproduced the smallest 124 million parameter model. But basically, this is just proving that the code base is correctly arranged. And I'm able to load the neural network weights that OpenAI has released later. So you can take a look at the finished code here in NanoGPT. But what I would like to do in this lecture is I would like to basically write this repository from scratch. So we're going to begin with an empty file, and we're going to define a transformer piece by piece. We're going to train it on the tiny Shakespeare dataset, and we'll see how we can then generate infinite Shakespeare. And of course, this can copy paste to any arbitrary text dataset that you like. But my goal really here is to just make you understand and appreciate how under the hood ChatGPT works. And really all that's required is a proficiency in Python and some basic understanding of calculus and statistics. And it would help if you also see my previous videos on the same YouTube channel, in particular my Make More series, where I define smaller and simpler neural network language models. So multi-allele perceptrons and so on. It really introduces the language modeling framework. And then here in this video, we're going to focus on the transformer neural network itself.
I find it surprising. I was expecting Andre to go through just the moving parts of what is shown in the model, in the paper. Transformer is all you need. And I was assuming that because in my previous experience, I did watch a similar video before. I did try to code it a little bit, and in that tutorial, it was a pretty good tutorial nonetheless, but we focused more on the implementation of the architecture. And frankly, I would be really, really happy with just that. But Andre seems to have taken it a step further, and he's introducing even a training script. Wow, that's crazy, and he's so nice to open source it. So I guess we're in good hands. Let's watch this tutorial further and see what we have.
Okay, so I created a new Google Colab Jupyter notebook here, and this will allow me to later easily share this code that we're going to develop together with you so you can follow along. So this will be in the video description later. Now, here I've just done some preliminaries. I downloaded the dataset, the tiny Shakespeare dataset, at this URL, and you can see that it's about a 1 megabyte file. Then here I open the input.txt file and just read in all the text as a string, and we see that we are working with 1 million characters roughly. And the first 1,000 characters, if we just print them out, are basically what you would expect. This is the first 1,000 characters of the tiny Shakespeare dataset, roughly up to here. So far so good. Next, we're going to take this text, and the text is a sequence of characters in Python. So when I call the set constructor on it, I'm just going to get the set of all the characters that...
I see that it's getting... I can see that it's getting a little hands-on, so let me try to follow along by opening up this collaboratory pardon me, technical stuff, yeah. And okay, nice. Andre exposed it on a collaboratory, so we don't have to clone the repository and stuff. And looks like in the first step, we are downloading the dataset. Okay, let's run this. authored by Google. Request access to your resource code. Okay, sure, let's go. Should be fine. I see it's downloading from his repository character recurrent neural network from his master branch on this folder tiny stage Shakespeare input text. Okay, let's go to GitHub. Let's check out my good sir Karpati. Okay, thank you so much. Let's go to, what's that again? Karpati char and then I don't see. There's so many variants. Yes, this one. Is it this one? Oh, this guy forked it from Andrej. Okay, that's not the one I'm looking for. I'm looking for the one by Karpati. Okay. There's so many people forked it. Maybe we should fork it too, but okay. Where is his main one? It's okay. Let's continue anyway.
That occur in this text. And then I call list on that to create a list of those characters instead of just a set, so that I have an arbitrary ordering. And then I sort that. So basically we get just all the characters that occur in the entire data set, and they're sorted. Now the number of them is going to be our vocabulary size. These are the possible elements of our sequences. And we see that when I print here the characters, there's 65 of them in total. There's a space character, and then all kinds of special characters, and then capitals and lowercase letters.
Okay, so Andrej explored the data set and got all the unique characters that we have in this text. And because we want our model to generate this text here, I guess, and maybe more, Andrej tried to get so-called the size, or rather the dimension of all the tokens that we have, where each token is a character. So in this case, we have 65 characters in this text. So the dimension of our the one-dimensional array that represents the characters would be of 65 rows or columns. I mean, one-dimensional, so I guess columns.
So that's our vocabulary, and that's the sort of like possible characters that the model can see or emit. Okay, so next we would like to develop some strategy to tokenize the input text. Now, when people say tokenize, they mean convert the raw text as a string to some sequence of integers according to some vocabulary of possible elements. So as an example, here we are going to be building a character level language model, so we're simply going to be translating individual characters into integers. So let me show you a chunk of code that sort of does that for us. So we're building both the encoder and the decoder, and let me just talk through what's happening here. When we encode an arbitrary text, like hi there, we're going to receive a list of integers that represents that string. So for example, 46, 47, etc. And then we also have the reverse mapping. So we can take this list and decode it to get back the exact same string. So it's really just like a translation to integers and back for arbitrary string. And for us, it is done on a character level. Now the way this was achieved is we just iterate over all the characters here.
Okay, I get it. So, this is a proof of concept. So understandably, Andrej didn't abstract the behavior of converting a string to an integer to a separate function, and from an integer to a string as well. And in this case, he came up with a nameless function to convert the string to a simple function, a simple nameless function called encode, that you can think of it as a callable, I guess. And it takes each character in a string and convert it to an integer by using this dictionary over here, and same for the decode. So I guess in this case with the print statements, he's able to check that if you decode it and encode it back, we should get the original string hide there, and sure enough, I guess we can think of it as a unit test. So yeah, it's pretty nice. Let's take a look. So we downloaded this, we read it to inspect it, we print the length of the data set, we print the first 1000 characters, we see all the characters that occur in this text, and we see the encode over here. Very nice. Okay, we might have to. Oh, I love how Andre de-risked this project by trying out the moving parts he needs to replicate this transformer architecture by testing it out here on his notebook. In production, this code over here would probably be abstracted to functions or classes, but I guess we don't have to do that yet. Let's do that together if Andre doesn't happen to do that, but it's okay. Thus far, Andre is really kind, really nice of him to give us everything that we need here. Let's continue.
Here and create a lookup table from the character to the integer and vice versa, and then to encode some string, we simply translate all the characters individually, and to decode it back, we use the reverse mapping and concatenate all of it. Now this is only one of many possible encodings, or many possible sort of tokenizers, and it's a very simple one. But there's many other schemas that people have come up with in practice. So for example, Google uses a sentence piece. So sentence piece will also encode text into integers, but in a different schema, and using a different vocabulary. And sentence piece is a subword sort of tokenizer. And what that means is that you're not encoding entire words, but you're not also encoding individual characters. It's
pretty similar to how GPT does it. So GPT, OpenAI GPT has their own tokenizer, and they do something similar as well. Yes, I love this UI. We come to this all the time. But if you say cheese, a little quirk. But if you have a word with a space in front, cheese by itself will be one token, and if you remove the space in front, then you get two tokens. Crazy stuff. But in this case, this is what we call a subword tokenizer, I guess, because chi is one token and ese is another token. But it's okay. Let's continue. I did not know about sentence piece, so I find this useful.
It's a subword unit level, and that's usually what's adopted in practice. For example, also OpenAI has this library called TickToken that uses a byte pair encoding tokenizer, and that's what GPT uses. And you can also just...
What does BPE mean, man? Byte pair encoding. Oh, I did not know about byte pair encoding ensures that most common words will be represented in the new vocabulary as a single token, while less common words will be broken down into two or more subword tokens. Oh yes, I mean, I guess it's the same as the subword tokenizer. I mean, subword tokenizers are a type of byte pair encoding is a type of subword tokenizer. So, and the objective is to reduce the number of tokens you really need in your vocabulary, so it reduces the dimensions of words. Yeah.
Just encode words into, like hello world, into a list of integers. So as an example, I'm using the TickToken library here. I'm getting the encoding for GPT-2, or that was used for GPT-2. Instead of just having 65 possible characters or tokens, they have 50,000 tokens.
Sorry, let me quickly test it out. Oh man, I thought to yes, I haven't installed TickToken, so let me just install it. Okay, Python 3. I do have it, right? Okay, let's check. Install pip install TickToken. Let's check whether if we have the Oh, they do expose it on the pip, so I should have been able to pip3 install tick token. Okay, we are installing it now. And tick token. Oh, what the heck? Did we just install that? Why can't you detect my package, man? Okay, okay, so I'm at my home. Let me just go to my parrot shop. Okay, and let's go to yeah, I guess let's go to GPT from scratch. Okay, nice. Guess we're here, and let's create a virtual environment. I've already created that, so previously. So now we're 3.9.6. Let's install tick token. And okay, now we're installing it. 2.3, import tick token. Nice, now it works. And let's get the okay. We're using GPT-2's encodings. Okay, wow, that took a long time. Let's just quickly check the type. Okay, so it's a class, and they abstracted all the encoding logic to this encoding class nicely for us, and we can encode hi there, and oh, what? Oh, sorry. I gave it EM. Oh, that's just bad naming. I'm sorry, I called it EMF. Let me just redefine it. So we're using GPT-2's tokenizer, and let's try encoding this hi there. Okay, nice. And how did he get the vocabulary? Okay, he accessed the attribute of this object and vocab. 50,257. Okay, let's continue.
And so when they encode the exact same string, hi there, we only get a list of 3 integers. But those integers are not between 0 and 64. They are between 0 and 50,256. So basically you can trade off the codebook size and the sequence lengths. So you can have very long sequences of integers with very small vocabularies, or you can have short sequences of integers with very large vocabularies. And so typically people use in practice these subword encodings, but I'd like to keep our tokenizer very simple. So we're using character level tokenizer, and that means that we have very small codebooks. We have very simple encode and decode functions.
I guess that makes sense now. Andrej made this project simple by using characters as tokens. I mean, it's going to suffer from the memory issue, but I guess for learning purposes, I would agree with Andrej. By using characters, he removes the prerequisite of understanding byte pair encodings or subword encoding. So very nice. I guess that really makes sense from a teaching perspective. For this whole project, there are multiple prerequisites, and by simplifying this, he removed that prerequisite, so it's easier for us.
But we do get very long sequences as a result. But that's the level at which we're going to stick with this lecture because it's the simplest thing. Okay, so now that we have an encoder and a decoder, effectively a tokenizer, we can tokenize the entire training set of Shakespeare. So here's a chunk of code that does that. And I'm going to start to use the PyTorch library, and specifically the torch.tensor from the PyTorch library. So we're going to take all of the text in Tiny Shakespeare, encode it, and then wrap it into a torch.tensor to get the data tensor. So here's what the data tensor looks like when I look at just the first 1,000 characters, or the 1,000 elements of it. So we see that we have a massive sequence of integers, and this sequence of integers here is basically an identical translation of the first 1,000 characters here. So I believe, for example, that 0 is a new line character, and maybe 1 is
0 is the new line character. Let's try this out. Okay, so you have it here already. So okay, let's insert a code cell above. Oh, sorry, that's below now, but that's okay. Let's validate that by decoding 0. Oh, of course, because decode is okay, it takes an iterable, so let me give it a list. Okay, yeah, he's right. Andrej is right. It's a new line character.
a space. Not 100% sure. But from now on, the entire data set of text is re-represented as it's just stretched out as a single very large sequence of integers. Let me do one more thing before we move on here. I'd like to separate out our data set into a train and a validation split. So in particular, we're going to take the first 90% of the data set and consider that to be the training data for the transformer. And we're going to withhold the last 10% at the end of it to be the validation data. And this will help us understand to what extent our model is overfitting. So we're going to basically hide and keep the validation data on the side, because we don't want just a perfect memorization of this exact Shakespeare. We want a neural network that sort of creates Shakespeare-like text. And so it should be fairly likely for it to produce the actual, like, stowed away true Shakespeare text. And so we're going to use this to get a sense of the overfitting. Okay, so now we would like to start plugging these text sequences or integer sequences into the transformer so that it can train and learn those patterns. Now, the important thing to realize is we're never going to actually feed the entire text into the transformer all at once. That would be computationally very expensive and prohibitive. So when we actually train a transformer on a lot of these datasets, we only work with chunks of the dataset. And when we train the transformer, we basically sample random little chunks out of the training set and train on just chunks at a time. And these chunks have basically some kind of a length and some maximum length. Now, the maximum length typically, at least in the code I usually write, is called block size. You can find it under different names like context.
In my prior experience, I've been calling OpenAI's training API. I did not know that we have block sizes for. I did not know that we sample text from the corpus to train them in chunk. So that's pretty surprising to me.
Length or something like that. Let's start with the block size of just 8. And let me look at the first trained data characters, the first block size +1 characters. I'll explain why +1 in a second. So this is the first 9 characters in the sequence, in the training set. Now what I'd like to point out is that when you sample a chunk of data like this, so say these 9 characters out of the training set, this actually has multiple examples packed into it. And that's because all of these characters follow each other. And so what this thing is going to say when we plug it into a transformer is we're going to actually simultaneously train it to make a prediction at every one of these positions. Now, in a chunk of 9 characters, there's actually 8 individual examples packed in there. So there's the example that in the context of 18, 47 likely comes next. In the context of 18 and 47, 56 comes next. In the context of 18, 47, 56, 57 can come next, and so on. So that's the 8 individual examples. Let me actually spell it out with code. So here's a chunk of code to illustrate. X are the inputs to the transformer. It will just be the first block size characters. Y will be the next block size characters. So it's offset by 1. And that's because Y are the targets for each position in the input. And then here I'm iterating over all the block size of 8. And the context is always all the characters in X up to T and including T. And the target is always the Tth character, but in the targets are.
That's okay. Oh, I would not know this detail. I knew that they had some form of masking where when we try to predict what's the next word for a sentence, this token or position should only see the tokens before. So everything that comes after it should be hidden, which makes sense when we write and when we say something, we say things based on what we have seen thus far, not in the future. I guess some people do that, but in this case, I guess we're doing something similar. In this case, the context is the words that are visible, I guess. Why? Oh, okay. And this works because X is the training data from position 0 all the way down to block size. So block size, I guess, in this case is 8. So this would be from index 0 to index 7. And Y would be from index 1 to index 8. Okay, that makes sense. Okay, so for t in range block size, we set the context to be t plus 1. In the first position, in the first iteration, t will be 0. So this would be x from 0 to 1 exclusive, so just 0. And the context in this case would just contain one character. For target, in this case, it would be y at position 0 as well, but this would correspond to the word at the first index since y starts from index 1. So in short, like for this example, in this case, in the first iteration, context would just contain 18 and target would contain 47. In the next iteration, I guess 2 iterations is enough to understand this. In the second iteration, t will be 1. So context will be from index 0 to 1 plus 1 equals 2, so 0 and 1. Context will be 18 and 47. Target would be y at position 1, so yt, so in this case target is referring to 56, so context is 1847 and target is 56. And following this tracing, we can see that the next one will be, for context it will be 1847 and 56, and the target would be 57. So yeah, it's masking. Yeah,
array Y. So let me just run this, and basically it spells out what I said in words. These are the 8 examples hidden in a chunk of 9 characters that we sampled from the training set. I want to mention one more thing. We trained on all the 8 examples here with context between 1 all the way up to context of block size. And we train on that not just for computational reasons because we happen to have the sequence already or something like that. It's not just done for efficiency. It's also done to make the transformer network be used to seeing contexts all the way from as little as 1 all the way to block size.
I did not know that. My implicit assumption was that the reason why we sample text instead of training the transformer with the whole text is because it's more efficient to train in chunks, I guess. I did not know, I would not have expected Andrej's point that we want to train the transformer with small snippets from size 1 to block size to make the transformer understand language in variable chunks of words. I found that pretty helpful and surprising.
And we'd like the transformer to be used to seeing everything in between. And that's going to be useful later during inference, because while we're sampling, we can start a sampling generation with as little as 1 character of context. And the transformer knows how to predict the next character with all the way up to just context of 1. And so then it can predict everything up to block size. And after block size, we have to start truncating, because the transformer will never receive more than block size inputs when it's predicting the next character. Okay, so we've looked at the time dimension of the tensors that are going to be feeding into the transformer. There's one more dimension to care about, and that is the batch dimension. And so as we're sampling these chunks of text, we're going to be actually, every time we're going to feed them into a transformer, we're going to have many batches of multiple chunks of text that are all like stacked up in a single tensor. And that's just done for efficiency, just so that we can keep the GPUs busy, because they are very good at parallel processing of data. And so we just want to process multiple chunks all at the same time. But those chunks are processed completely independently, they don't talk to each other, and so on. So let me basically just generalize this and introduce a batch dimension. Here's a chunk of code. Let me just run it, and then I'm going to explain what it does. So here, because we're going to start sampling random locations in the dataset to pull chunks from, I am setting the seed so that in the random number generator, so that the numbers I see here are going to be the same numbers you see later if you try to reproduce this. Now the batch size here is how many independent sequences we are processing every forward-backward pass of the transformer. The block size, as I explained, is the maximum context length to make those predictions. So let's say batch size 4, block size 8, and then here's how we get batch for any arbitrary split. If the split is a training split, then we're going to look at train data, otherwise at val data. That gives us the data array. And then when I generate random positions to grab a chunk out of, I actually generate batch size number of random offsets. So because this is 4, ix is going to be 4 numbers that are randomly generated between 0 and len of data minus block size. So it's just random offsets into the training set. And then x's, as I explained, are the first block.
Sorry, I'm not too sure what torch ran in does. Let's quickly test that out. Pip install torch. Not ideal, I know. Like I guess it's not ideal because I'm not installing our dependencies in the requirements.txt file. But it's okay. I guess we will deal with this first. As we install, let's take a look at the torch ran int. Returns a tensor filled with random integers generated uniformly between low and high. Okay, so 2 parameters followed by size. Shape of tensor is defined by variable argument size. And because Andrej provided a tuple of 1 dimension only consisting of batch size, I guess ix here, oh man, it'd be nice if there were type hints, man. But okay, let's take a look at this. Split is a string, and data in this case is a list of a string, I guess. Wait, train data is I mean, I understand this is a notebook, so you wouldn't expect. Oh yes, this is a torch tensor, of course. So torch.tensor. Let me quickly understand this type over here. I mean, it's not ideal, but import torch. Data equals to, oh wow, data equals to torch.tensor. Encode cheese. And data type will be torch.long. Oh, of course, I need the encode lambda function. Okay, let's just, I mean, encode gives back an array of numbers, so 1, 2, 3, 4, 5. So, oh, no module name numpy. Okay, I guess they needed numpy, but let's check data. And we get back a tensor. Let's get a type of data. And it's a tensor object. Okay. So data here is a torch.tensor. And the train data over here is a subset of data. So it looks like torch tensor overwritten the get item, the hidden get item dunder method, I guess, to support this operation. Just details. And what this means is train data out here is really a torch.tensor, and this is a torch.tensor as well. Yeah, so just to be sure, let's try slicing this by 5 as well. Oh, sorry, made a mistake there. 1. Yes, we do get a tensor, so sliced tensor goes to this, and if we do the type of sliced tensor, get a torch tensor object. Okay, makes sense. Block size is 8. Train data here is also a torch tensor. This is also a torch tensor. Okay, not really necessary for me to give this type hints now, but what this means is I got this wrong. This is not really a list of a string. This is really a torch tensor object. This is torch random int. So let's try out random int. So let's give it 5 minus 5, and let's give it a batch size of 2. So this should give me a torch tensor from 0 to 5, I guess, because I didn't provide the start. Sorry, I didn't provide the start here, so I'm expecting randint to take in 5 as the high here, yeah, and it will go from 0 to 5. 1 above the highest integer to be drawn from the distribution, so it means 0 to 4. 0 to 4, I guess. If I provide 5, then it should give me 0 to 4. So let's quickly validate that. 2, 2, 0, 3, 0, 4, yep. I mean, this is not a definitive proof, but we can see there's no 5 here, so documentation makes sense. Okay, so this gives back a torch tensor of batch size. Okay, torch.stack. I'm sorry, I'm very rusty with torch. It's been quite some time, but let me stack data I to I plus block size for I in index. Okay, so we have slices of block size for I in index. Okay, so we are slicing, we're getting random slices. Then what does stack do? Stack, I guess, is either horizontal stack or it's either a horizontal stack or vertical stack. I think it's a vertical stack. Woo! Let's give this a shot. So torch.stack. Let's try stacking. Okay, let's just creating a first tensor. This would be torch.rand int 0 to 4, size 2, and first tensor, second tensor, same thing. And now we have first tensor and second tensor. And what happens if we do torch.stack first tensor and second tensor? Or is that how? Oh, sequence of tensors, sorry. So this would have failed if I pass both in as 2 separate arguments. And okay, they stack them horizontally. Okay, so they stack this horizontally, so you get a 2-dimensional torch tensor, where you get same for this as well. Okay, and this returns back x and y, so this really gives us back a tuple of a torch tensor. Okay, that makes sense. And get batch. Okay, okay, nice, we got it. Oh, you're complaining because I don't have tuple defined, but that's from typing import tuple. Actually, since we're using Python 3.9, Python 3.9 allows us to do this, so that's fine. If you're using Python 3.8 though, you have no choice but to import this tuple from the typing library, and this typing library would have this from Python 3.6, FYI. Okay, let's continue. I'm sorry for the side quest.
Block size.
I was really trying to understand get batch here, and what I did was I played around with the methods. I understood that I was missing some prerequisites. I was missing what exactly torch.randin does. I'm missing what does torch.stack does. So it was a little hard for me to understand what's going on. And data and index, I wasn't sure exactly what's the type here as well. So as you see, like I sucked it up and scrolled up and checked the types systematically. So as a rule of thumb, if you feel stuck at any point of time, remember that we are allowed to take pauses to understand the prerequisites, and we try to chip at each of these prerequisites one by one by doing some experiments. So I hope that was useful. Let's continue this video.
Characters starting at I. The y's are the offset by 1 of that, so just add +1. And then we're going to get those chunks for every one of integers I in ix and use a torch.stack to take all those one-dimensional tensors, as we saw here, and we're going to stack them up as rows. And so they all become a row in a 4x8 tensor. So here's what I'm printing then. When I sample a batch xb and yb, the inputs to the transformer now are, the input x is the 4x8 tensor, 4 rows of 8 columns, and each one of these is a chunk of the training set. And then the targets here are in the associated array y, and they will come in to the transformer all the way at the end to create the loss function. So they will give us the correct answer for every single position inside x. And then these are the 4 independent rows. So spelled out as we did before, this 4x8 array
I didn't get that, so let me
offset by
this.
1 of that, so just add +1. And then we're going to get those chunks for every one of integers I in ix and use a torch.stack to take all those one-dimensional tensors, as we saw here, and we're going to stack them up as rows. And so they all become a row in a 4x8 tensor. So here's what I'm printing then. When I sample a batch xb and yb, the inputs to the transformer now are, the input x is the 4x8 tensor, 4 rows of 8 columns, and each one of these is a chunk of the training set. And then the targets here are in the associated array y, and they will come in to the transformer all the way at the end to create the loss function. So they will give us the correct answer for every single position inside x. And then these are the 4 independent rows. So spelled out as we did before, this 4x8 array contains a total of 32 examples, and they're completely independent as far as the transformer is concerned. So when the input is 24, the target is 43, or rather 43 here in the y array. When the input is 24, 43, the target is 58. When the input is 24, 43, 58, the target is 5, etc. Or like when it is a 52, 58, 1, the target is 58. Right, so you can sort of see this spelled out. These are the 32 independent examples packed in to a single batch of the input x, and then the desired targets are in y. And so now this integer tensor of x is going to feed into the transformer, and that transformer is going to simultaneously process all these examples and then look up the correct integers to predict in every one of these positions in the tensor y. Okay, so now that we have our batch of input that we'd like to feed into a transformer, let's start basically feeding this into neural networks. Now we're going to start off with the simplest possible neural network, which in the case of language modeling, in my opinion, is the bigram language model. And we've covered the bigram language model in my Make More series in a lot of depth. And so here I'm going to sort of go faster, and let's just implement the PyTorch module directly that implements the bigram language model. So I'm importing the PyTorch NN module for reproducibility. And then here I'm constructing a bigram language model, which is a subclass of NN module. And then I'm calling it, and I'm passing in the inputs and the targets. And I'm just printing. Now when the inputs and targets come here, you see that I'm just taking the index, the inputs x here, which I renamed to idx, and I'm just passing them into this token embedding table. So what's going on here is that here in the constructor, we are creating a token embedding table, and it is of size vocab size by vocab size. And we're using nn.embedding, which is a very thin wrapper around basically a tensor.
Did Torch NN module override a hidden method so that you can call this class like this? Wow. Okay. What's that dunder method though? Let's do a quick search. Dunder method for calling a specific method when using class. I'm not sure if I asked that question correctly, but there are hidden methods in Python that allows us to override the behavior of operators and also do something weird like this. Like we can see that on this line over here, we can call the class, we call the object here, sorry, this is an initialized object. But for this object, we could use it like it's a function. So what is that? What's that dunder method for that? For her. Oh, must be wrapper. REPR. Must be wrapper. Let's try it out. Am I in GPT from scratch? Yes, I am. Okay, let's try creating our own class. Just test wrapper. In itself, let's name. Okay, def wrapper, test wrapper name. And what was that? Like they were able to call the forward method automatically. They were able to call the forward method automatically by calling the object like this. So I'm going to have a hypothesis. My hypothesis is that it's the wrapper dunder method that is responsible for that. And if we want this similar behavior, I would need to overwrite it. So I would have to create a simple, let's call this number adder. And this is going to be a class that is responsible for adding two numbers together. So I'm going to it's not really a great example, but I'm going to call this add. I'm going to create a add method, and it's going to take in two integers, and it'll return back a plus b. And for this wrapper over here, I'm going to call add instead. So self.add and 1 2, and I guess for this wrapper you would expect a and b as well. And let's see. Oh. What? Okay, let's check what Python wrapper does. Yeah. Oh, it represents the person, but then how does torch and then module works then? I guess I could have went ahead with that anyway, but or even better, I can just import from torch import nn.module torch.nn import module, and let's take a look at the class here. So you have a wrapper, I guess. Oh, so my hypothesis was wrong. Then yeah, it doesn't look like it's the wrapper method that is responsible for calling forward, because I don't see any forward in this implementation over here. So how is this forward used then? Forward and okay, just a buffer. Where's the forward method? Oh, it's not here. What? It's not here. Module. Okay. Where is forward here? I am expecting an implementation of forward here. Okay, let's see. Wow, I'm really surprised. I was expecting a forward method under the module class. Yeah, module classes in Torch are supposed to have the forward method. So how, what? What the, okay, it's taking too much time, so I'm going to continue anyway, but I will try to see exactly how we make class support a behavior like this. Why is it that for an object you do not have to call a method forward here with the dot forward method, and you can just do it like that? So just do one final search: how to make an object call a method in Python without calling the method. No, that's not really it, right? Okay, final gamble. I'm gonna make a gamble and just hope that there's a dunder method list that lets us understand what are the methods that we have. Other operators. Oh, call. It's call. Okay, nice. It's call. Let's try it out. Call, and just like this. So let's do if name equals to main. Then let's add a test. Yeah, we really don't need this constructor. So let's just do this. And number adder add. Actually, let's just do this. So let's create the object. My object equals to number adder. I'm sorry. Okay, so let's create this object here, and let's try doing this and see if this returns back 3 as expected. So let's Python 3 main.py. Okay, we got it. Yes, so that was our hypothesis. Our hypothesis was that Torch neural network module overrides the call method, and that's why the call method calls forward somehow. Okay, makes sense. Yeah, they have the overwritten call dunder method here. Okay, I'm sorry, frankly that wasn't necessary. It was a side quest for curiosity's sake. So specifically I was wondering why Torch neural network tensor over here can be called like this, but we realized that you can do that if you make classes override the dunder call method.
Of shape vocab size by vocab size. And what's happening here is that when we pass IDX here, every single integer in our input is going to refer to this embedding table and is going to pluck out a row of that embedding table corresponding to its index. So 24 here will go into the embedding table and will pluck out the...
Okay, so we have covered the introduction, the reading and exploring of data, tokenization, train and value split, and the data loader as well. So for the next part of this video, looks like we'll be going through a simple baseline, and that's the bigram language model as you see over here. So we are using a very simple classical model, a bigram, and in this case, the bigram over here, if I'm not mistaken, it calculates the probability of a given word, of a word given the previous word. If I'm not mistaken, but I might be wrong. I have to do some searching. And for this video, I guess it's a good start. So that's pretty much it for this video. For this part. For the subsequent videos, I'll be continuing on this lecture, and let's see what we get. So with that, that's it for today. I hope you enjoyed the video. A little long-winded, but I hope that this was a raw experience of how we would understand a tutorial. So with that, I will see you in the next one.